Okay, so let's have a look at this third one here. If you haven't got it out, you should get it out.
I got it out.
Excellent.
What are we getting over?
This one from yesterday.
I needed this guy.
You need it?
Yeah.
Did you go? Yesterday, I showed you how to convert from Elches to coulombs and vice versa, and we also looked at when the little droplet wasn't suspended. So we're going to sort of review all that, throw it all together here, and do this last problem. Millikan observed a droplet of unknown charge accelerating at minus 2.3. He determined the mass of the droplet to be 5.3 times 10 to the minus 6. The electric field strength was 3.6 times 10 to the 6. The question is, what charge is on the droplet and how many elementary charges is this? Okay, so this one is a little bit different from yesterday because this one's giving you the acceleration. We're not working towards that. We're going sort of backwards a little bit. Okay, Cole?
Yeah.
So maybe let's just write down what we know here. A is minus 2.3. We've got the mass, 5.3 times 10 to the minus 6. The E value is 3.6 times 10 to the 6. And we're solving for Q, and then we're going to have to convert that to elementary charges. Okay? So we've got A, we've got M, we got E, we're looking for Q. We're working backwards. Okay? It's quite likely in an electric field like this, Lane, seriously, Matt, time to focus. Got the weight force up, we've got the electric force up here. Okay, number one question, which one of those two forces is bigger? Forces.
They're the same.
I drew them the same, but that's not, how do I know that's not true? Because it's accelerating. So it's which, okay, let's back up even more. Which way is this thing going, up or down? Down, because it's negative, which means that the gravitational force is the bigger one, right? If there was no electric force at all, the weight force would be the only one, it would be accelerating at minus 9.8. So the FE is the sort of the drag, like the friction. Is it ever a bad idea to figure out the weight force at the start? No. Always a good one to sort of get you started. Mass times gravity. 5.3 times 10 to the minus 6. Is the negative part of the 9.8 important here? Is the direction important here?
Yeah.
Yes. That's the question you ask yourself. If the direction is important, then the negative is important. 5.3. It's going.
Are you always going to use that? It's not every one of these.
Pretty much, yeah. Like Cole said, it really is a free mark. So it's always a good idea to do that. Well, it gets you started, right? You know you can do it, right? If you're having trouble getting started, do that first, and then go from there. So I got 5.19.
Ha! Here's the answer.
5.
Really distracting from my learning.
Mr. Beck, can you explain how you already, I don't understand how you get the phone.
I count on my calculator. Yeah. Count the decimal places.
How'd you get that negative 5? Oh, because you moved it 5.
I moved it over 5 decimal places.
You always have to put the full number, like 5.19.
You traditionally we sort of put 1 to the left and 2 to the right. Scientific notation is usually 2 to the right. That's
Well,
it.
instead of doing that, we could just...
Well, you could if you want to write the whole thing out, yeah. But if it's like a lot of zeros, it's right. Sure. Okay, so that's the weight force. Do we know what the electric force is? Well, the electric force is F equals QE. I don't know the charge, do I? So I can't do that. Okay, so in fact, that's how I'm going to end up by finding the charge, right? I know the acceleration. I know the mass. What will that tell me? That'll tell me F net. F net is equal to MA. Mass 5.3 times 10 to the minus 6, and our acceleration is minus 2.3. Is the negative important? Is the direction of the net force important?
Yep.
Yep. Minus minus 1.22 times 10 to the, count them over, Lane.
1, 2, 3, 4, 5.
Okay.
Why isn't the other one negative?
Yeah, it should be, should I? I was just looking at that. We made the weight force negative. Okay, so if the weight force is minus 5.19, but the net force is minus 1.22, that's because there's a force up that's sort of putting a drag on that, right?
So what's the weight force?
5.19 times 10 to the minus 5, minus 5.
That's why she's accelerating because of the weight force.
If there was no electric force, then it would be accelerating at minus 9.8. Okay? But because it's accelerating at only minus 2.3, there's some drag on it here. Okay, so to figure out how much that drag is, F net is electric plus weight forces. And this net force is minus 1.22 times 10 to the minus 5. And the reason that that negative is important is because of this step right here. Let me just make myself some more room here. Yeah, I was just thinking, I bet your kids would be able to like to do that. Just moving it over. What is the electric force? Hey, that's what we're trying to solve for. What is the weight force? Negative 5.19 times 10 to the minus 5. And yes, those negatives are important. And now we're going to take that minus 5.19 to the other side. It's going to become positive. Right, so I'm going to have 5.19 times 10 to the minus 5, subtract 1.22 times 10 to the minus 5, and that's going to equal my FE. What does it equal? Well, I had it and then I pressed it on the correctly.
You did. Like that?
No, I didn't.
I get 3.97 times 10 to the minus 5. We're almost done. We're almost done. So this is like, Graham, this is like the frictional force that's dragging it, right? Slowing it down. But we want to know what charge provides that. Okay, so we're going to go back to E equals F over Q. The E value, I don't know what it was, 3.6 times 10 to the 6. This FE is the same as this FE right here. And we're going to solve for Q. Your calculator should likely go straight to scientific notation for you, because it's an extremely small number, 1.1 times 10 to the minus 11. Just stay with me, you guys, for another couple minutes. What is that? What is the units for that, Cole? Are you checking online there to find out what the units are? Because you're not very good at hiding what you're doing. No, you're not. I know what you're doing.
Oh, what are you doing?
How about you stand up for me? Yeah, gotcha. 1.1 times 10 to the minus 11 coulombs.
Yeah, you're most rapid. Take that, right?
Can we save those questions for just like another minute and a half?
Yeah, probably.
Okay, thanks. The final question was, how many elementary charges is this? So how do I convert coulombs to elementary charges? This is from yesterday, right? So those of you that were already yesterday should watch. 1 elementary charge is 1.6 times 10 to the minus 19 coulombs. So if I've got 1.1 times 10 to the minus 11, X elementary charges. 1.1 times 10 to the minus 11. Right? This is what we did yesterday in the board thing. Remember, we set up that ratio. 1 elementary charge is 1.6 times 10 to the minus 19. So X
Equals.
is 1.1 times 10 to the 11. Cross multiply. And you're going to have 1.6 times 10 to the minus 19. X is equal to 1 times that. And you're going to end up dividing, aren't you? Do you get a really giant number?
What does that say up there, Pat?
1 L.
1 elch, 1 elementary charge.
How do you spell that?
ELCH. Elementary charge, ELCH.
Yeah.
You should get a really big number. I get 6.88. Should it be a really big number? Yeah, you've got 1.1 times 10 to the minus 11 coulombs, but 1 elch is 1.6 times 10 to the minus 19. It's going to be times 10 to the 1, 2, 3, 4, 5, 6, 7. No. You've got 68 million electrons. 6.88, well, I just put a 7 there, didn't I? Should be times 10 to the 7. 6.88 times 10 to the 7 electrons. That's a lot of electrons. Okay, so that's a good example of sort of one where you work backwards instead of giving you the charge to find the acceleration. We're sort of working backwards. This would be more sort of what someone might do in a lab, based on that acceleration, work backwards and find the charge. Okay? A problem similar to that could be, yeah. I'll give you a sort of an outline of what type of problems you can expect. Okay, I'm going to give you the rest of the period. You can work on your Millikan project if you need to. You can work on practice problems if you need to. You can do the quiz if you want to. I'd like it in by the end of tomorrow. Okay?
Quiz.
I handed the one that says quiz on it.
You have to do all those questions.
There's only 4.
Oh, this one.
Only 4.
Yeah.
Tomorrow I'm going to discuss some applications of electrostatics and give you some time. We have to draw electric fields as well. So that's Tuesday. No, that's a Thursday. Let's aim for Monday.
For what?
For the test, yeah.
Tuesday.
Aim for Monday, and we'll reevaluate at the end of the week. We're aiming for Monday, Cole.
What?
Okay, go.